All right, strap in, everyone, because we are diving deep into a real head scratcher today. Dark matter. We're talking about decades of research, a mountain of scientific papers, and a whole lot of mystery. And you know me, I can't resist a good mystery. So let's untangle this invisible universe, shall we?
You said it, a mystery. I mean, try to wrap your head around this.
Oh.
The majority of matter in the universe is completely invisible to us.
Okay, yeah, you've got my attention. We're talking about the fundamental ingredients of the cosmos, and we're basically clueless. How do we even know it's out there if we can't see it?
It all started with these little discrepancies, like tiny hints that something just wasn't adding up in the grand cosmic scheme of things. Back in the 1930s, there was this astronomer, Fritz Zwicky, and he was looking at a galaxy cluster.
A galaxy cluster, so like a massive city of galaxies, right?
Exactly. And he noticed that these galaxies were moving way too fast. I mean, way faster than the visible matter's gravity could explain.
So, like, imagine watching a car just zoom around a corner way too fast, almost like defying physics. You'd think to yourself, hold on, something's not right here?
Exactly. And that's what Zwicky thought. His observations hinted that there was some hidden mass, something unseen, holding it all together. Now, fast forward a few decades to the 1970s, and Vera Rubin enters the scene. She was studying how galaxies rotate, particularly how fast stars orbit the galactic center.
And I'm guessing she found some speed demons out there, too.
You got it. Rubin found that stars on the outskirts of galaxies were moving way faster than they should be if only the visible matter was calling the shots. Imagine a merry-go-round where the horses on the outer edge are moving at the same speed as those closer to the center. Something's not right. This finding suggested that there must be a halo of invisible matter, what we now call dark matter, providing that extra gravitational pull.
Okay, so two separate observations, decades apart, pointing to the same mind-blowing conclusion. We're missing a huge part of the picture. It's like finding out there's a whole invisible city running right alongside our own. So how do we go from these early clues to actually mapping out this unseen world?
Scientists use this clever tool called the mass-to-light ratio. It basically tells you how much mass there is in a system compared to how much light it gives off.
Yeah.
When you see a high mass-to-light ratio, it's like a big neon sign flashing dark matter here.
So we're basically weighing galaxies and galaxy clusters to figure out how much of this invisible stuff is hiding within. That is some seriously impressive cosmic detective work.
It really is. Yeah, and it's not just about galaxies spinning too fast. There's a whole bunch of evidence pointing to dark matter. Take gravitational lensing, for example.
Okay, now that sounds like something straight out of science fiction.
It might sound like it, but it's very real. Einstein himself predicted it. Imagine a bowling ball on a trampoline, how it distorts the fabric. Massive objects, including dark matter, warp the fabric of space-time, bending light around them. It acts like a giant cosmic magnifying glass, distorting and magnifying the light from objects behind them.
So we're talking about using the very fabric of the universe as a magnifying glass to study something we can't even see. My mind is officially blown.
And it gets even wilder. One of the compelling pieces of evidence comes from the Bullet Cluster. It's this cosmic crash site where two galaxy clusters collided. What's fascinating is that the hot, visible gas, which should make up most of the mass, well, got separated from the main gravitational pull. It's like seeing the shadow of a ghost after the ghost itself has moved on. This separation strongly suggests that a huge chunk of the mass is invisible, hardly interacting with itself or the visible matter.
Okay, that's getting kind of spooky. Like we're catching glimpses of something pulling the strings from behind the scenes. But hold on, we're forgetting about something, aren't we? What about that faint echo of the Big Bang, the cosmic microwave background? Surely that has something to say about dark matter too, right?
You're absolutely right. We can't forget about the CMB. This radiation is like a baby picture of the universe, showing us what it was made of just a few 100,000 years after the Big Bang. And guess what? It screams dark matter. The specific pattern of those temperature fluctuations in the CMB tells us that dark matter was already a major player back then, influencing how the universe evolved.
Okay, so we've got galaxies spinning too fast, light bending around invisible objects, and even the afterglow of the Big Bang whispering about dark matter. It's like the universe is playing a giant game of cosmic charades, and every clue points to the same answer.
And yet, with all this evidence, the biggest question remains unanswered. What exactly is dark matter made of?
All right, so we've established there's a giant invisible elephant in the room. What are the top contenders for its true identity? So we've got a mountain of evidence pointing to something massive lurking in the shadows of the cosmos, but it's like trying to assemble a puzzle with only half the pieces. What are the main suspects in this cosmic detective story?
Well, for a long time, the leading theory has revolved around something called WIMPs, weakly interacting massive particles.
WIMPs. Okay, that doesn't sound very impressive for something that's basically holding the universe together.
Haha. Yeah, the name doesn't exactly scream cosmic powerhouse. But trust me, they're heavy hitters in the world of particle physics. The massive part means they'd carry a lot of weight, potentially much heavier than familiar particles like protons and neutrons. But the weakly interacting part, well, that's where it gets tricky. WIMPs would barely interact with normal matter. We're talking ghost-like particles, basically.
Okay, so these are like our cosmic ninjas, silently shaping the universe as they slip through walls unnoticed.
Precisely. They'd mostly exert their influence through gravity. Their weight would dictate how galaxies form and clusters assemble.
So we're on the hunt for these elusive heavyweights, but WIMPs haven't been the only game in town, right? What other candidates have scientists been looking into?
Right, there are other possibilities. One really interesting alternative is the axion, a particle so incredibly light it makes an electron look huge. What's fascinating is that axions could have been produced in the very early universe with properties that make them perfect for dark matter.
So while WIMPs are like the strong, silent type, axions are more like a massive, unseen crowd, potentially swarming the universe in unimaginable numbers.
Yeah, that's a great way to put it. And then there are sterile neutrinos. Regular neutrinos are already masters at avoiding interaction, rarely interacting with matter at all. But sterile neutrinos, they take it to a whole other level.
We're talking about a particle even more elusive than a neutrino. That's like trying to catch a whisper in a tornado.
You got it. But even those faint whispers could have a huge impact. And we can't forget about models like the inert Higgs doublet, which suggests there's a completely different type of Higgs boson out there, one that interacts with regular matter even less than the one we already know about.
A whole other Higgs boson. It's like finding a secret room in your house that you never knew existed. But with so many possible suspects, how do we even begin to narrow down the search?
There are two main approaches: direct detection and indirect detection. Direct detection is kind of like setting a trap in the dark. We build these incredibly sensitive experiments, often burying them deep underground to shield them from stray cosmic rays, and wait for a dark matter particle to, well, bump into something.
So we're basically waiting for a ghost to knock over a vase in a cosmic seance.
In a way, yeah. Experiments like CDMS, Edelweiss, and CREST are all racing to be the first to detect one of these telltale interactions. They're looking for the tiniest tremors, the slightest release of energy, as a dark matter particle grazes a nucleus.
Talk about a delicate touch. So what about indirect detection? What are we looking for there?
Indirect detection is more like searching for footprints, looking for the evidence left behind after dark matter interactions. We're talking about the debris from when dark matter particles collide and annihilate.
So instead of catching the culprit red-handed, we're analyzing the crime scene.
Precisely. Some of the most promising clues come in the form of high-energy particles, like positrons, gamma rays, and neutrinos. Take the positron excess observed by the Pamela experiment, for instance. They found way more high-energy positrons than expected, and you know what? Dark matter annihilation could be the culprit, especially if a mechanism known as the Sommerfeld enhancement is at play.
Sommerfeld enhancement. Okay, that sounds complicated.
It is a bit technical, but bear with me because here's the cool part. This enhancement suggests that dark matter particles might be feeling a new kind of force, a dark force that only they experience. This force could be pulling them closer together, increasing their chances of annihilation, and therefore boosting the signals we might detect.
Okay, so not only are we dealing with invisible matter, but it might be playing by its own set of rules, a whole other set of forces that we're completely oblivious to. It's like discovering a secret code hidden within the very fabric of reality.
Exactly, and figuring out that code could completely change our understanding of the universe. And speaking of signals, gamma rays are another exciting avenue. Unlike charged particles, which get deflected by magnetic fields, gamma rays travel straight from their source. This means if we see an excess coming from places where dark matter is concentrated, like the centers of galaxies, that would be a strong sign.
So gamma rays are like cosmic lighthouses, allowing us to trace their beams back to these invisible masses of dark matter.
That's a great analogy. And then there are neutrinos, the true ghosts of the particle world. They can travel across the entire universe without interacting with anything, carrying information from the most extreme and inaccessible places even places light can't escape from.
So while gamma rays are like our cosmic lighthouses, neutrinos are the ultimate messengers, potentially carrying secrets directly from the heart of dark matter itself.
Exactly. Neutrino detectors like IceCube are constantly scanning for any sign of dark matter annihilation. It's a monumental task, like trying to hear a whisper in the middle of a rock concert, but the potential payoff is huge.
It's incredible to think that we've built these massive, sophisticated experiments, both underground and in space, all to understand something we can't even see or touch. It really speaks to the power of human curiosity, don't you think?
Absolutely. And even with all this focus on finding dark matter, we have to acknowledge that there are other theories out there too. Some physicists believe that we might not need exotic new particles after all. Maybe it's our understanding of gravity that needs an update.
So instead of searching for invisible particles, maybe we need to rethink the fundamental force that governs the universe. Tell me more. So if we're not fully convinced about these invisible particles, where does that leave us? Are we saying that we need to rewrite the laws of gravity?
Well, some physicists are exploring that possibility. There's this concept called MOND, short for Modified Newtonian Dynamics, and that's exactly what it proposes. The idea is that maybe gravity on those really huge scales of galaxies and galaxy clusters doesn't quite work the way Newton described it. It's like tweaking the equation a bit, adding a new factor that accounts for those weird observations we've been talking about.
So instead of introducing this whole idea of invisible matter, MOND says that gravity just gets a little wonky at vast distances.
You could say that. It's a bit like saying the rules of a game change when you move from a small field to a massive stadium. And the funny thing is, MOND actually does a pretty good job of explaining those strange galaxy rotation curves we talked about earlier.
So if MOND can explain those observations, why isn't everyone on board? Seems simpler than inventing a whole new type of matter.
Yeah, I mean, simplicity has its appeal, for sure. But there's a catch. While MOND can handle some observations, it runs into trouble with others. It's like having a key that only unlocks some of the doors in a house.
Okay, so which doors is MOND having trouble unlocking?
Remember the bullet cluster, that epic cosmic collision we talked about? MOND struggles to explain why the gravitational lensing, the warping of space-time, is in a different spot than the visible matter. It's like seeing a shadow in a completely different place from the object casting it. That discrepancy is a strong point in favor of dark matter being a real clustered substance.
So it seems like we're back to the drawing board, or maybe back to those invisible particles. But even if we accept that dark matter is out there sculpting the universe as we speak, where does that leave us? What's the ultimate fate of a universe governed by these invisible forces?
Now, that's where things get truly mind-blowing. For a long time, we thought the universe's fate was a coin toss, really, expand forever, or collapse back in on itself in a big crunch. The answer depended on how much stuff, visible and dark matter combined, was pulling against the expansion of the universe.
A cosmic tug of war with the fate of everything hanging in the balance. That's a pretty intense image.
You can say that again. But then astronomers stumbled upon something that totally changed the game. It turned out the expansion of the universe wasn't just continuing, it was speeding up. Like someone hit the accelerator on the cosmic engine.
Whoa, what a plot twist. So instead of slowing down, the universe is actually gaining speed. What unseen force could possibly be driving this cosmic joyride?
We call it dark energy. It's like this inherent repulsive force woven into the very fabric of space-time, pushing everything farther and farther apart. And here's the kicker. It's not just some small, insignificant effect. Current estimates say that dark energy makes up a mind-boggling 68% of the universe's total energy.
Okay, so we've gone from a universe dominated by invisible matter to one ruled by invisible energy. It makes you feel pretty small, huh?
It definitely puts things into perspective, that's for sure. And you know what? This discovery totally changes the game when it comes to the universe's fate. With dark energy in the driver's seat, the expansion will likely continue forever.
So instead of a big crunch, we're headed for a big freeze. A universe growing ever colder and more spread out as everything drifts further apart.
That's the leading theory right now.
Yeah.
Eventually, stars will burn out, galaxies will fade beyond our reach, and the universe will become this vast, cold, and incredibly lonely place.
It's both awe-inspiring and a little bit depressing thinking about these cosmic timescales. But I guess that's what we're here for, right? To explore these incredible concepts and try to understand our place in the grand scheme of things.
I couldn't agree more. And even though it seems like the universe's fate is set, there's still so much we don't know. The true nature of dark matter, the properties of dark energy, these are still massive areas of research. Who knows what amazing discoveries are waiting for us, what new questions we'll have to grapple with.
That's the beauty of it all, isn't it? It's like we've opened one door only to find 1,000 more, each with its own set of mysteries waiting to be unraveled.
Absolutely. And as we keep exploring, keep digging deeper into the mysteries of the universe, we can't help but feel a sense of awe for its sheer scale and complexity.
Well, this deep dive has been an incredible journey. We've traveled from the tiniest particles to the largest structures in existence, all to try to understand these invisible forces that shape our universe. We've wrestled with WIMPs and axions, explored the bending of light, the echoes of the Big Bang, and even questioned the very nature of gravity itself.
It's been an absolute pleasure unraveling these cosmic puzzles with you. And hey, who knows, maybe someday you'll be the one to finally crack the code of the invisible universe.
One can only hope. But until then, we'll keep asking questions, searching for answers, and marveling at the incredible mysteries that still linger out there in the cosmic dark. Thanks for joining us on this mind-blowing deep dive. Until next time.